The focus of this video will be on the STEM-SAT1 CubeSat project. STEM-SAT1 will be launched in early 2024. It'll be the first satellite launched by Athens State University. STEM-SAT1 will be riding aboard Vaya's Dauntless orbital launch vehicle. This rocket uses a more eco-friendly fuel made using the conversion of recycled thermoplastics. STEM-SAT1 will be deployed with several other satellites as a rideshare option. Satellites generally weigh roughly 100 kilograms to 420,000 kilograms. The image on the left is a Starlink satellite and is roughly 260 kilograms. The image on the right is the International Space Station, the largest satellite in orbit, and weighs roughly 420,000 kilograms. Our 3-unit cube satellite stands 4 by 4 by 12 inches and weighs roughly 9 pounds. The image on the left is STEM-SAT1 burst so that we can see the components. The dipole antennas are made of tape measure, which can coil and then unravel when the satellite has been deployed. There are 4 deployable double-sided solar panels. There are receiving and transmitting antennas located on opposite sides of the spacecraft for isolation purposes. STEM-SAT1 has high-capacity lithium-based batteries and will use NiCads as an alternative. STEM-SAT1 will have an altitude of 500 kilometers in low Earth orbit and will have an inclination of 59 degrees. It will rebroadcast low frequency and very low frequency signals in the 434 megahertz band. The first mission objective is to introduce students K through 12 and older into space-based disciplines. Activities include, but are not limited to, mission planning, ground station operations, data reduction and correlation, hardware and software development, building and testing, and launch operations. The second mission objective is to collect, store, and retransmit low-frequency and very low-frequency signals from space. The ionosphere blocks low-frequency and very low-frequency signals from reaching the ground, so there's currently no way to receive these signals. A mission like this, retrieving low-frequency and very low-frequency signals, is relatively new, and findings will be abundant. When STEM-SAT1 is in the sunlight, the main emissions we'll be looking for are solar radio bursts type 2 and 3. They're generally associated with solar flares and coronal mass ejections. The type 2 burst has a slower drift rate and usually lasts around 10 to 30 minutes, whereas the type 3 burst has a rapid drift rate and only lasts around 10 seconds to a minute. Type 2 bursts are generally associated with coronal mass ejections and are relatively rare compared to the number of events taking place on the Sun. Type 3 bursts are generally caused by streams of electrons traveling from the Sun's surface all the way out to 1 astronomical unit. They're typically emitted by solar flares and are the most common impulsive radio signature from the Sun. When STEM-SAT1 is out of the sunlight, we will turn our ears towards Jupiter and its moons. We will receive signals from Jupiter's moon Io, raining electrons down on Jupiter. This process is also known as the electron cyclotron maser. We will also be able to listen for emissions from supermassive black holes, gamma ray bursts, radio pulsars, binary stars, deep space cosmic radiation, emissions where hydrogen reionization and first galaxies were born. The possibilities we'll find are endless. Let's talk about how to retrieve these transmissions. The STEM-SAT1 team included a link from Radio Adventurer and also instructions on how to build your own Yagi antenna. You'll need a wooden boom, 11 wires, a handheld radio, a coax cable, and coax adapters. The process is simple and they're relatively low. Space environments will affect STEM-SAT1 just as it does anything else that exits the atmosphere. The main precautions that we need to take are thermal blankets, redundancy, and recovery algorithms. The vacuum environment holds concerns for our satellite such as pressure differentials, solar UV degradation, contamination, and outgassing. The debye sheath should be able to protect STEM-SAT1 from particulates for the most part, but we need to ensure surface cleanliness in order to minimize risks. The neutral environment poses less of a risk than the other environments as long as STEM-SAT is oriented in the correct direction in order to reduce aerodynamic drag. Atomic oxygen and spacecraft glow-resistant materials with high sputtering thresholds are recommended. The plasmid environment poses a risk such that electronics will be affected if precautions aren't taken. The exterior surface conductivity must be uniform, and all electronic boxes should have electromagnetic shielding. The radiation environment poses a more serious risk. STEM-SAT1 needs to have recovery algorithms for latch-up and upset. It needs redundancy in size, selection, and shielding for the entire spacecraft. The micrometeoroid and orbital debris environment also poses a larger threat. There are more than 3,000 satellites currently in LEO. There are more than 36,500 debris objects more than 4 inches wide. There are more than 4 million debris objects between 0.4 and 4 inches. And there are more than 330 million debris objects between 0.04 inches and 0.4 inches. The amount of orbital debris should fall with solar maximum approaching. However, it has been estimated that roughly 58,000 additional satellites could be launched by 2030, primarily in LEO. Cube satellites tend to decay more rapidly in comparison to other satellites. The aerodynamic drag will force STEM-SAT1 back into Earth's atmosphere, where it will fully ablate, posing no threat to the escalating space debris issue. The information acquired will be stored and available to everyone.